Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. Here you have information about online seminars and study manuals for exams PFM, IFM, and LTAM that I offer. I direct the Actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to make a tax-deductible donation to support our students, please go to smarturl.it/help-ISU actuary. Here's the problem for today for exam P on probability. This year, the number of accidents x at an amusement park has probability generating function p sub x of t equal to e to the minus 0.2 times 1 minus t were defined. The amusement park owner's insurance company reimburses up to a maximum of one accident this year. Let y be the number of unreimbursed accidents. Determine the probability generating function p sub y of t of the number of unreimbursed accidents at this amusement park this year were defined. And here's the solution. So remember that the definition of a probability generating function p sub x of t is e to the expected value of t to the x. So a value at t is expected value of t to the x. For a discrete random variable with non-negative integers as values, this specifically means that it's a probability that x is 0 plus the sum from n equal 1 to plus infinity of t to the nth times the probability that x is n. And the reason why I separated this probability that x is 0 because then we have this issue of interpreting the value at 0 when t is 0 to the power 0. So let's just, of course, note that if t is 0, then 0 to the x, that's just 0. But that's not really how we ended up interpreting this because when t is 0, this function ends up being equal to the probability that x is 0. So we can write this as, in this case, for the negative integers as values, as probability that x is 0 plus the sum from n equal 1 to plus infinity of t to the n times the probability that x is n. In this case, in this problem, the moment generating function is e to the minus 0.2 times 1 minus t. That's the same as e to the minus 0.2 plus 0.2t, so it's e to the minus 0.2 times 1 plus the sum from n equal to 0 to plus infinity of 0.2t to the power n over n factorial. So we can write this as e to the minus 0.2 plus the sum from n equal 1 to plus infinity of 0.2 to the nth times t to the nth over e to the 0.2 times n factorial. In particular, we see immediately that the probability that x is 0 is e to the minus 0.2, and then the probability that x is n for larger values, not for 0, but for 1 and 2 and so on, and that is equal to 0.2 to the nth over e to the 0.02 times n factorial. Actually, it does hold for n equal to 0. That's still it's true, so I'll just leave it like that. Furthermore, we have y equals 0 with probability equal to the sum of probabilities that x is 0 and x is 1, because unreimbursed losses are 0 when the number of accidents, or unreimbursed accidents is 0 if a number of accidents is 0 or 1. Only starting with 2 accidents, we have unreimbursed accidents. So, and that's equal to e to the minus 0.02 plus 0.2 to the first over e to the 0.02 times 1 factorial. And that's the same as 1.2 e to the minus 0.02. While for k equal to 2, 3, and so on, the probability that y is equal to k is the probability that x is equal to k plus 1, which is 0.2 to the k plus 1 over e to the 0.02 times k plus 1 factorial. And now we just calculate this. So we want the probability generating function of y at t. We write it as the sum from k equals 0 to plus infinity of t to the k times probability that y is equal to k. Although technically it's kind of nicer to clearly see what's going on by writing that this is the probability that y is 0 plus, because of course in case of t equal to 0 you end up with this 0 to 0, which is interpreted to be 1. That's the whole interpretation in this case. Plus the sum from k equal 1 to plus infinity of t to the k times probability that y is equal to k. And then we ask ourselves, what is the probability that y is 0? That's the probability that x is 0 plus probability that x is 1. And in the summation, we have the sum from k equal 1 to plus infinity of t to the k times the probability that x is equal to k plus 1. Here's the probability for those cases. If we take away 1, so we start with higher values of x, starting at 2, then that's when x is equal to 2, y is equal to 1. So we have x starting at k plus x equal to k plus 1 for the value of y equal to k. And that's equal to the probability that x is 0 plus the sum from k equals 0 to plus infinity of t to the k times the probability that x is equal to k plus 1. Now we start counting at 0, and we substitute n equal to k plus 1, and this becomes a probability that x is 0 plus the sum from n equal 1 to plus infinity of t to the n minus 1 times probability that x is n. Then we factor out that from t to the n minus 1, we just put 1 over t in front, and this becomes probability that x is 0 plus 1 over t times the sum from n equal 1 to plus infinity of t to the nth times probability that x is equal to n. Okay, if we just add one term, then we will have a regular probability generating function for x. So we do that, but it's multiplied by 1 over t. We add that one term and we subtract it before that expression. So what we end up with is probability that x is 0, which is e to the minus 0.2, minus 1 over t times the probability that x is 0, which is e to the minus 0.2, plus 1 over t multiplied by the probability generating function of x, which we know to be e to the minus 0.2 times 1 minus t. And then we combine the terms and we get e to the minus 0.2 times t minus 1 plus e to the minus 0.2. Now this time 0.2 is multiplied by 1 minus t. Before it was e to the minus 0.2, the whole expression was multiplied by t minus 1. And the whole thing is divided by t. That's actually answer E. Please remember this is copyrighted material. The problem itself comes from Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.